Good morning, everyone. Thanks for sending your project proposals. I plan to read them later this week and then send individual feedback by email to everyone. So I want to finish off where we were last time, and then we're going to start a new topic, which is compressed sensing, which is going to be now different from this large-scale linear algebra stuff. Although, as you'll see, they're going to be related. Okay, so lots of these different topics we cover in this class are actually related. So last time we covered three different methods of using subspace embeddings for regression, for least squares regression. The first one was the simplest one. If you have an epsilon subspace embedding, you get epsilon approximate regression. Okay. And then the second one was this iterative approach, where you basically well-condition the matrix to speed up gradient descent. Okay. And the third method is this one, where you really only need, well, is this legible right here? The bottom? Not very much? Okay, so basically, let's say your regression problem is minimize the L2 norm of Sx minus b, right? What we said was, as long as pi satisfies two deterministic conditions, then you'll get a good approximation by doing sketch and solve, okay? Those two conditions were, first of all, write the SVD for S, U double prime, sigma double prime, V double prime transpose. I just put these primes because when we actually continue with the class, I will care about some other U sigma V transpose. So pi should just be a half subspace embedding for the column space of S, which is the column space of U double prime. And it should satisfy this approximate matrix multiplication guarantee with error square root epsilon over D, where S has D columns, or the rank of S is D. Okay? And if those two conditions hold, then we showed, well, you can decompose this thing as this plus that in the terminology of last time. And this W is the optimal regression error. So W is B minus Sx star. X star is the actual optimal solution to the regression problem. So this is opt. And then you have some extra error term, which you want to say is small. And what we argued last time was that this error term is at most this thingy, which looks a lot like approximate matrix multiplication. So because it has this property, this approximate matrix multiplication property, you get a good error bound. Okay. So that's how we ended last time. Yeah. D? S is n by D, sorry. So yeah, S has D columns. Yeah. So D just needs to be something that's at least the rank of S. Okay. So now today I'm going to show you how to use subspace embeddings for low rank approximation. And it's going to look a lot like, once you write things down, it's going to look a lot like regression method 3. Okay, and then we're going to move into compressed sensing. So let's do this. Okay, so what's the basic idea of low rank approximation? The basic idea is you have some huge matrix A, which let's say looks something like this. Think now of like both dimensions being huge. Okay, one is bigger than the other, let's say. Actually, that's not even necessary for what I'm going to say. What I'm going to say is going to speed things up even if both dimensions are roughly the same order. But let's say that it's an n by D matrix where n number of rows is, say, like these are the users, and D are like the attributes. Okay, so for example, people who have Netflix accounts and movies, okay, and then each number is like how they rated it. But let's pretend now that we know all the numbers. Okay. And the idea behind low rank approximation is that users are actually low dimensional. Okay, what do I mean by that? I mean, yes, there are D attributes here, like how did they rate movie 1, how did they rate movie 2, et cetera. But actually, there are only a few hidden attributes that actually matter and determine everything, up to some error maybe. So for example, this person really likes horror movies and doesn't like comedy so much, and loves movies in the 50s, from the 50s. Okay, so there are these very few dimensions that aren't explicit in the matrix, but they kind of govern the way the entire matrix behaves. Okay, so each row is actually some linear combination of these basic types. Okay, a type is a horror movie lover or a lover of movies from the 50s. And then every row, every user is some kind of linear combination of those basic types. Okay? And each user is, let's say not exactly, because it's not going to be exactly low rank, but each user is close to a linear combination of basic types. Okay, and then our goal is to basically figure out what these hidden types are, these eigentypes. Right? These are basically the singular vectors of the matrix A. We want to find this low rank structure. Okay, so pictorially, basically what I'm saying is that A is actually something like a product of two matrices. This is n by k. Think of k as like tiny, and then k by d. And these are users, and these are the movies. Okay. So for each user, there's some linear combination of the basic types. Okay, these hidden types, and each movie also is some kind of combination of these. Each movie can be represented in the basis of these types. Okay. And this is the kind of thing that I want to discover. Okay. So, I mean, there's lots of work on matrix factorization. So, one thing that is a little weird here is if you just say linear combination, these numbers could be negative. So many people have argued that kind of as I've motivated it now, the thing that makes most intuitive sense is that you should look for a non-negative matrix factorization where each user is actually a non-negative combination of basic types. Like I'm 30% horror movie lover and I'm 70% comedy lover, or something like that. What does it mean if I'm 0.3 movie lover and then minus 0.2 something else and then minus something else, right? So, but nevertheless, this low rank approximation is still a very widely used thing. Okay. Okay, so our goal is to basically find this kind of low rank approximation. Okay.
So we want to find the matrix.
I should say approximately. Sorry?
So we're looking to find this factorization.
We're looking to find a rank K matrix. So this product is a rank K matrix, right? So I changed my equals to approximately equals. So we're going to assume that our matrix isn't exactly rank K. It's not true that there are exactly K hidden types of users, but it's approximately true. So I have this approximate equality, and what I'd like to do is basically find the best factorization of this form. Yeah.
Is it true that if you stuck like an invertible K by K matrix and its inverse in the middle, you get exactly the same approximation? So there's infinitely many solutions.
Yeah. So I mean, you're saying basically I can put in the middle, put like m inverse, and m multiplies this, m multiplies that.
Yeah. So you don't feel like must make some other assumptions.
So right. So actually, right now, what we're going to talk about today is not actually decomposing it like this. We're just going to say find a rank K matrix that approximates. Find one matrix.
We're happy with any solution.
Yeah, just find me any rank K matrix which approximates A. So our goal Yeah, we want the product. So our goal is to compute AK, which is the argmin over matrices B of rank at most K of basically A minus B. Okay. So B, for us, AK would be the product of these two matrices. Okay. And today we're going to look at Frobenius norm.
Wouldn't the product resolve in that matrix anyways?
No, because so the point is this product actually is rank K because I have K columns here. Whereas, so this is not equality. This is approximate equality. So in actuality, if you wanted to write A as some kind of factorized matrix, the number of columns you would need in actuality is the rank of A. So A might be high rank. It might even be full rank. But I just assume that it's close to a low rank matrix. So what I want to do is I want to find the closest low rank matrix to A. So find this product which makes this approximate as good as possible. You're given A, yeah, you're given A as input. So you have your database, your Amazon or whoever you are, Netflix. You have your matrix of attributes and users given to you, and you want to find this low rank structure. And then once you have the low rank structure, maybe you can learn things about your users, make predictions, cluster them, whatever. Okay. So this is what we'd like to do. And it's a theorem that basically, this is called the Eckart. It's usually called the Eckart-Young theorem, even though apparently this is a wrong attribution because I think Schmidt from Graham Schmidt actually proved this theorem like decades before this. But it says that if A is U sigma V transpose, then AK is UK sigma K VK transpose. What does that mean? What I mean by that is if U is this matrix, let's say n by d, then UK is equal to this matrix. So n by d, but basically only keep the first k columns. It's this matrix. That's UK. It's an n by k matrix. Just keep the top k singular vectors, and sigma looks like sigma 1 up to sigma d, where sigma k is somewhere over here. And then sigma k is just, take this part. Just basically only keep the top k singular values, only keep the top k singular vectors in U and V. So this is a rank k matrix, right? UK has k columns, VK has k columns, sigma k is a k by k matrix. Question about, you look like you're... Yeah, sorry, yeah. So I should have said where sigma 1 is bigger than or equal to sigma 2 is bigger than or equal to that. Yeah. Okay. So what does this tell us? Well, if we can compute the SVD. So by the way, today, our goal here is not, we're not gonna actually spit out this matrix AK. We're going to spit out a factorization of AK. We're going to spit out the SVD of AK. Okay, and that's going to be our output. What this tells us is we can compute AK in time OND squared. This is the SVD time, right? Once you have the SVD, getting the best low rank approximation is easy. That's what this is telling us. But just like regression, I don't want to spend SVD time. I want to do things faster. So theorem Okay, so first, actually, before I write the theorem, let me write a definition. So for matrices A and B, the projection onto A of B is the projection of the columns of B onto the column space of A. Okay, so you replace each column of B with the projection of that column. Okay, and then also proj AK of B, or A comma K, is just proj A K. I mean the best rank K approximation. So in general, whenever I put a K on the outside of a matrix, I mean like the best rank K approximation, at least for the rest of this proof. And now let me write the theorem. So define A tilde K as being the projection proj A pi transpose K A. Okay, so project the columns of A onto the column space of A pi transpose, and then take the best rank K approximation of that. Then we have that A minus A tilde K for Frobenius norm is at most 1 plus O of epsilon times the actual opt, as long as pi satisfies certain conditions. So first of all, pi should be a 1/2 subspace embedding for the column space of VK transpose, or for a column space of VK, I guess. And 2, we should have square root epsilon over K approximate matrix multiplication under Frobenius norm for the matrix for pi, basically for VK transpose A minus AK. So remember, when I say that we have approximate matrix multiplication for A transpose B, what I mean is pi A transpose pi B is close to A transpose B. So what I'm saying is pi VK transpose pi this matrix should be close to what the actual product is. And the actual product is 0. Right? Because remember in the SVD, the columns of V are orthogonal, or they're orthonormal, right? So A minus AK is basically all the stuff that I chopped off. It's all the stuff that's orthogonal to VK, right? So this is actually 0. Oh, actually, to make the 0, I should put a transpose here. Oh, that's Frobenius norm. Yeah. Right. So, okay. So we'll prove this. It's gonna look very similar to method 3. In fact, the conditions look very similar to method 3. But why is this? Okay, let's parse this and understand why this gives a faster algorithm. Okay. So I said that there is a matrix A tilde K which does well. Why can we get our hands on A tilde K quickly? Okay, that's the question. We want to beat SVD time, which is ND squared. Okay. So let's look at computing proj A pi transpose K A. So first of all, pi is going to be an m by n matrix, or actually for us m by d, let's say. And m is going to be something like, well, how many rows do we need from, say, a Gaussian matrix, a random sign matrix, to satisfy these conditions? Well, vk is a rank k. It has k columns, right? So we want to preserve a k-dimensional subspace. So using an up to a factor of a half. So for that, we need O of k columns. I mean, O of k rows of pi. M is going to be at least O of k. And then to satisfy this condition, remember, if you want AMM with error alpha, you basically need 1 over alpha squared rows. So for this, we need k over epsilon. So number 2 is the bottleneck in terms of m. So m is going to be O of k over epsilon. Okay. So first of all, we need to multiply A pi transpose. But that's fast because we can use a fast subspace embedding, right? We can use a sparse subspace embedding or whatever, the Hadamard-based approach, the fast Fourier-based approach. So that's fast. And then we need to compute the SVD A pi transpose, and let's call that U prime sigma prime V prime transpose. How much time is that? Well, A pi transpose is an n by m matrix. So it's nm squared. So this is nk squared over epsilon squared time. Okay. Well, if d is really big and k is not as big, then that's not so bad, maybe. Okay. Then what we want is we want U prime transpose A. We want the best rank k approximation of that, which is the same thing since U prime has orthonormal columns as U prime transpose A k. Computing U prime transpose A, well, U prime, what are the dimensions of U prime? U prime is n by m. So this thing here, just computing U prime transpose A takes time m and d. So we've at least replaced one of the d's with an m, which is like k over epsilon. In fact, let me show you now, you can actually replace both of the d's with m. You can get something that's more like nm squared. How do you do that? And the idea is to use regression. Note that we don't actually need U prime transpose A k. We can just approximate it. So what do we want? So what does this thing mean, right? What does this mean, or what does this mean? It means we want the best rank k approximation in the column space of this matrix. The column space of this matrix is the same as the column space of U prime. So we want the best rank k approximation in the column space of U prime, right? So what we actually want is kind of x to be the argmin of U prime x minus a Frobenius norm, where the rank of x is at most k. That's what we actually want. Or alternatively, forget the rank constraint, and then what we do is we output ux k, which is the same as ux k. But the point is, we don't actually need x exactly. We can approximate. This looks a lot like regression. Imagine if A was actually a vector instead of a matrix, and this is L2 norm. This is exactly a regression problem, and then we're going to treat it that way. So, last lecture we just talked about regression when B is a vector, but the same exact analyses apply if B happened to be a matrix instead, and you're looking at Frobenius norm. Frobenius norm squared is just the sum of L2 norm squareds. Okay. So we'll use fast regression to get x tilde such that u prime x tilde minus a Frobenius norm squared is at most 1 plus epsilon. 1 plus epsilon times the actual, let's call this x star, times u prime x star minus a Frobenius norm squared. And then we'll output u prime x tilde k. And what are the dimensions of x tilde? Well, x tilde is actually, I guess, k over, it's m by d, which is k over epsilon by d. And I need to compute its SVD. So I can compute its SVD in time, which is like k squared times d. K squared over epsilon squared times d. So altogether, let's say that x tilde is like u x tilde sigma x tilde v k v x tilde transpose. We're going to output as our decomposition u prime u x tilde sigma x tilde v x tilde transpose. That's going to be our final output. Okay, so I just wanted to say a word about why this is good. Okay, why we're actually speeding things up. I mean, you didn't, you didn't need to do this half of the board. You could have settled for this. This is already faster. If k over epsilon is smaller than d, this is already faster than nd squared. But I just wanted to point out, in fact, you can improve that even a little bit more by approximately doing this generalized regression problem. So this is usually called, well, in some literature it's called generalized regression because A is now a matrix instead of a vector. But the principle is basically the same as what you've seen before. Okay? Questions? Yeah.
Is it obvious why adding and introducing an error doesn't hurt you once you take the rank K approximation?
Oh, you're saying yes, this is true, but once I take the rank K approximation, why?
I mean, I believe it, but like, is it?
Yeah, I think. Now have I confused myself? I see your question. Yeah, let me think about that. Yeah, I'm pretty sure it's okay, but let me think offline for a minute and I'll respond. Okay, so now let me prove the theorem. Good. So what I'd like to do is I'd like to bound I'd like to bound a minus a tilde k. Good. So so let y be the column space of the projection onto a pi transpose ak. Okay. And P is the orthogonal projection onto Y. Okay. Then this is the thing we're outputting. We're outputting A minus proj A pi transpose K of A Now, what is this matrix? This is the best rank K approximation in the column space of A pi transpose. So this is certainly at most A minus PA for Venus norm squared, because PA is some rank K approximation. PA is some rank K sorry, PA is a rank K matrix. Okay, it is a rank K matrix that lives in the column space of A pi transpose. So certainly the optimal rank K approximation does better than PA does. Okay. And then now I can decompose A as AK plus AK bar. Okay, so let me call this thing V transpose times AK bar transpose. By AK bar, I just mean A minus AK. It's all the other stuff. It's the error. So I can decompose this as AK minus PAK plus AK bar minus PAK bar. Right? Because these two, this is definitely the sum of these two things, and they're orthogonal to each other. So the fact that they're orthogonal means that, right, in general, remember that trace for Venus norm squared of M is the trace of M transpose M, right? So if you expand, in our case, M is the matrix A minus PA. If you expand M as this plus this, then, and you kind of expand out this trace, you'll have terms that are orthogonal, that have orthogonal column spaces, and then the dot product is 0, basically. And what you're left with is this. Okay, so now this term is equal to identity minus that projection operator, AK bar. And identity minus projection is just itself a projection. It's a projection onto the orthogonal space, right? And projection operators can't increase norms. They can't increase Frobenius norms. So this is certainly at most AK bar Frobenius norm squared, right? Which is exactly what we're happy with. This is opt, right? This is A minus AK. So the goal then is to show that this part here is at most epsilon times opt squared. Which, by the way, looks a lot like that, right? Basically, this AK bar is a matrix W as opposed to a vector W from last time. And now kind of beta is also, think of beta as like a matrix. And we want to show that beta has small Frobenius norm squared. Okay, so want to show that AK minus PAK Frobenius norm squared is at most like epsilon times that thingy. Okay. So kind of what is P, right? So remember before that, kind of when we were doing regression, we said that, well, did I define this? So remember if A, let me just define some notation. If A is U sigma V transpose, then A pseudo inverse, definition, A pseudo inverse is V sigma inverse U transpose. And A pseudo inverse is the projection operator onto A. Right? Because if you multiply these two things together, V transpose V is identity, sigma sigma inverse is identity, you have UU transpose, which is exactly the projection operator. Okay? So what did we say it's the projection operator on? It's the projection operator onto the column space of that matrix Okay, so we can now write down what that means. Okay, so let's do that. So the projection of AK, that's the thing we care about, is A pi transpose of this thingy AK. Okay, so the point is, forget about P for a second. The projection onto the column space of A pi transpose of AK is exactly this matrix. Okay, so if you want to project this matrix, if you want to project AK onto the column space of this matrix, well, it's its own best approximation in that space. Okay, so basically now what we have here is AK minus A pi transpose AK for Benioff norm squared. Okay. The projection of the matrix is the best, right? So this thing here, oh, this is a plus pseudo inverse. This matrix here is the best rank K approximation to AK in the column space of A pi transpose. So in particular, if we replace this matrix with another rank K matrix in the column space of A pi transpose, it can only have bigger norm. So let's do that. We're going to bound this by AK minus A pi transpose AK pi transpose AK for Benioff norm squared. So I just replace this part with this. So again, this is another rank K matrix in the column space of A pi transpose. Okay. And now what I want to say is, well, this is equal to, I really want to view this as regression. So let me just sum over, well, let me also, if you take a matrix and take its transpose, they have the same Frobenius norms. So let me just take the transpose so it looks like something slightly more familiar. This is equal to AK transpose minus AK transpose pi AK transpose pseudo inverse pi A transpose. This is a K. And this is equal to the sum over I of AK transpose from 1 to n, AK transpose I minus AK transpose pi AK transpose pseudo inverse pi A transpose I L2 norm squared. So basically I just summed over the columns of, so AK is an n by k matrix, or sorry, AK is an n by d matrix. So its transpose is d by n. I summed over its columns. It has n columns. Okay, so now this looks like a mouthful, but there's like one key insight in this proof, and the key insight is that this is exactly regression. Why is this exactly regression? Basically, I just want to say we've already analyzed this. So imagine regression problem. X star is the argmin of AK transpose AK transpose X minus A transpose I. Okay. So the optimal thing to do is AK transpose X should be the projection onto the column space of AK transpose of this matrix, right? And the projection of this matrix onto that one is exactly AK, right? But if you're doing sketch and solve like we're doing, or if you're doing regression method 3, then you're going to have that X tilde is not going to be, so X star is going to actually be the kind of AK transpose, X star is going to be AK transpose pseudo inverse A transpose I. That's the actual optimal thing to do. But if you do sketch and solve, instead what you're going to do is you're going to get X tilde, which is going to be pi A K transpose pseudo inverse A transpose I, which implies that AK transpose X tilde is going to be exactly AK transpose times this matrix. Pi A transpose. Sorry, there's a pi here. And right, that is exactly, if I did this correctly, that's exactly that. Okay. So now we're just basically bounding regression errors. Okay. And so now kind of in that notation, basically my matrix S looks like AK. My matrix U double prime is equal to VK, right? Because the columns of U should form an orthonormal basis for the column space of S. The column space of AK transpose, right? The column space of AK is UK. The column space of AK transpose is VK, because I transpose it. So that's that. And kind of, we have a beta I and a WI for each I from 1 to n now. Okay. Good. And so what I have last time is basically now beta I squared is at most 2 pi VK transpose pi WI L2 norm squared. Right? So if I sum over I now, I can write this as kind of 2 times pi VK transpose pi capital W for Frobenius norm squared, where W just has WI's as its columns. And good. That's it. Questions? Why does sketch and solve give what? Oh, right. So you're saying, so I'm saying if you were to do sketch and solve on this regression problem, then the actual cost. So if you were to do sketch and solve on this regression problem, you would get x tilde being this thingy, which means that AK transpose x tilde would be exactly what we got over there, which means this thingy over here is exactly like kind of what your cost would be if you had done sketch and solve to solve that regression problem. Okay, and then what I want to do is I want to apply regression method 3. I'm just basically reusing the analysis of regression method 3 and saying, if I bound that error there using this analysis, then I get good error. Yeah.
Why do you need the bottom calculation? Like, it seems like the minute we say our solution is going to be basically the norm of beta squared, a bunch of norms of beta squared.
Yeah.
And then the next line of the result from last time is that those norms are divided by epsilon op squared, basically like op I squared, right?
Yeah. So I guess instead what I would have to say is that it satisfies like n different AMMs simultaneously, and then you might be tempted to union bound or something. I just want to say that you can really encode this as a single AMM, where you just make this matrix W have WIs as its columns. Yeah. Okay. So let me change gears a little bit. Right, and the point is, by the fact that I have my root epsilon over k AMM, maybe I should just write that. Right, so pi vk transpose pi w is the same thing as pi vk transpose pi w minus vk transpose w, because this is 0. Actually, yeah. And by the AMM property, this thing is at most root epsilon over k times the Frobenius norm of vk times the Frobenius norm of w. This is root k. And then it's squared, so squared. And that's epsilon times w Frobenius norm squared. And notice that in our case, w, this matrix W, when you actually do this column by column thing, is none other than A transpose minus AK transpose. Okay, so let me say a couple words about low-rank approximation, things that we're not going to actually cover, but maybe I should make you aware of. One thing is there's been some interest in work where the low-rank matrix you find. So so there's been some matrix in like, I want to find few columns of A, such that if I find the best rank K approximation just in the span of those columns, it provides good error. Okay, so there are a couple works that do this. So Boutsidis, Draneas. So by the way, this is the end of that proof. So Boutsidis, Draneas, and Magdon Ismail as well as Guruswamy Sinop. Say it's possible to find T being some like O of k over epsilon columns C of A such that A minus CC minus the projection onto those columns A is small. Okay. And by small, I mean, say it's at most 1 plus epsilon times A minus AK. So if you want to say that there are actually few columns of the data that explain everything, then you can find that. And these are polynomial time algorithms. Another thing I want to say is related to something you've seen on a p-set, which is k-means clustering. Where note k-means clustering is actually some kind of low-rank approximation. Why? So you had a p-set problem on k-means clustering, I believe, right? Remember what we said? So k-means, the points are x1 up to xn in Rd. So let me define a matrix A, which is just this matrix, x1 transpose xn transpose. Given a partition P, which is P1, Pk of the points into K clusters, I believe one part of your p-set said if you have a partition into clusters, the best centers in those partition, the best centers for each cluster are basically the centroids. Just average all the points in the cluster. Then so define a matrix xp, which is, this matrix is going to be in n by k, such that if you look at xpij, this is equal to 1 over the square root of the size of pj if I is in the cluster j and 0 otherwise. If you ignore the columns of this matrix that are 0, let's pretend that let's not pretend none of the partitions are actually 0. Let's pretend that I mean, there's really no advantage in k-means to use less than k clusters, because if you put a point in its own cluster, you're only going to do just as well. So let's say that we don't have any empty clusters. Then you can convince yourself that xp transpose xp is the identity. Okay. So, and also, you can convince yourself that rho I of xp transpose A is exactly the centroid of the cluster that xi belongs to. Which implies that the k-means cost, k-means is to compute let me put it like this, to compute the optimal partition, which minimizes A minus XP transpose A. What is this? It's the projection of A onto some k-dimensional subspace, right? So k-means is actually find the best rank k approximation to A, but you're not allowed to use any rank k approximation you want. It has to be a restricted one of this form. It has to look like XP transpose A, where XP looks like one of those matrices. So this is constrained rank k approximation. Okay, and so you can ask yourself, well, kind of, rather than minimize this, what if I did dimensionality reduction? What if I put a pi transpose here, and I put a pi transpose here? Basically what I'm doing is I'm reducing the number of dimensions d down to something, right? Usually we talked about putting pi on the left. That means reducing the number of rows. Now I'm putting pi on the right. I'm reducing the number of columns. So I'm reducing the dimension of these xi's. That's exactly what you studied in your PSET problem, right? If I reduce the dimension of the xi's to log n dimensions by JL, then I still get a good approximation. So here the question is, do I really need log n dimensions? Okay. And okay, I'll inject the correct citation in the notes, but kind of this low rank approximating connection was observed in I think Boutsits et al. I'll inject the exact reference in the notes. And it was earlier, but the journal version just came out recently, I believe. Used also in Cohen et al. Stock 15. Pi can have m being O of k over epsilon squared for 1 plus epsilon approximation. And m can be log k over epsilon squared for a 9 plus epsilon. Okay, so what this paper by Cohen et al. Showed is that if you pick pi to map down to k, roughly k dimensions, k over epsilon squared dimensions, and solve the new k-means problem, then you'll get, solve that optimally. That partition you find will be within 1 plus epsilon of the best partition for the actual k-means instance. And if you map down to log k over epsilon squared, it'll be within a constant, 9 plus epsilon. So now just think, you can get arbitrarily close to a 9 approximation. So there's an open question. Okay. Conceivably, that's possible. I should mention that this result, this k over epsilon squared, it's for a more general problem, which is constrained rank k approximation. So suppose I give you a constraint set that contains only some k-dimensional subspaces, and I say, find me the best rank k approximation that lives in one of those subspaces. Then they say, if you map to k over epsilon squared and do sketch and solve, you'll get that. This result is specifically for k-means. This log k is specifically for k-means. It can't even be true in general. Okay, you can, for example, if you try to do unconstrained rank k approximation, that's a special case where the constraint set is empty, or where everything is allowed, then you really do need to map to k dimensions. Otherwise, you lose rank, and then you're screwed. Okay, so anyway, so yeah, so I just thought I'd leave you with that, and that's all that we're going to talk about in class for this kind of large-scale linear algebra stuff. Although there's a lot of nice results out there, but there's just not enough time to cover everything. So, questions about that? About anything? Okay. Actually, I basically gave as a p-set problem 2 years ago to reprove the Boutsidis et al. Boutsidis, what they showed was if you map to k over epsilon dimensions, you get a 2 plus epsilon approximation. Okay. And I gave that as a p-set problem, and I gave it as a final project idea to show that actually k dimensions can get, roughly k dimensions can get you down to 1 plus epsilon approximation. And at least, well, I think that paper had 5 authors, and 3 of them were in the class, although they didn't solve it during the class. But so you can don't be scared of problems for your final projects. Okay. So I'm done with that topic, and we're going to move into another topic which will consume the next few lectures, I guess, which is compressed sensing. Okay, and I only have about 20 minutes left, so I'll kind of set things up so that next time we can just prove stuff. Okay. So the basic idea is as follows. We have, let me use a different piece of chalk. Okay, we have a vector x in Rn, which is compressible. What do I mean by compressible? Well, a sparse vector is definitely compressible. If it's n-dimensional but only has k non-zero entries, then I can specify the vector to you by just writing down those k entries and telling you the locations. But for us, compressible is going to mean not just sparse, but say compressibility is not going to be binary. Yes, it's compressible. No, it's not. It's going to be a level of compression. So for us, a vector is compressible, or its quality of compressibility is how close is it to a k-sparse vector. Okay? So I'll fix a particular k, and it's perfectly compressible if it's k-sparse. If it has small distance to a k-sparse vector, I'll still say that it's somewhat compressible. Okay? And the idea is, so x compressible if, let's say, x tail k small. I haven't specified the norm. And what do I mean by x tail k? I think I've used this notation before when we were talking about count min sketch. Basically, look at the vector x. Look at the largest k coordinates, the largest k entries of x in magnitude. Those are what I'll call the head coordinates. And then all the other n minus k coordinates are the tail. Okay? So for example, if x is 5, 0.1, minus 17, or 2, then these are part of the head, and these are part of the tail. 2 because I kept the top 2 coordinate entries. Okay. And what the goal of compressed sensing is to acquire compressible signals using few measurements. So the number of measurements we need will be kind of related to the compressibility, the number of measures. So what I'd like to say is if it's compressible, I can basically do k measurements and then get the signal. recover the signal from those k measurements. Okay, so goal is to approximately, let's say, recover x from few linear measurements. Okay. And what I mean by linear measurements, I mean we'll get alpha 1 dot x, we'll get alpha 2 dot x, we'll get alpha m dot x. And given these m numbers, I want to approximately recover x. By the way, I can just view this as being pi x, where pi is other way. So what I want is to recover x tilde from pi x such that x minus x tilde subnorm, let's call this norm 1. Well, we're always going to deal with LP and LP norms here. So let's say the LP norm of this is at most some constant epsilon PQ times x tail. That's what I'd actually like to do. For some P and Q and some epsilon, some constant that depends on these things. Notice that if x actually is k-sparse, then the tail is the 0 vector, which means that there's 0 error. So if it actually is k-sparse, I should recover it. If it's not exactly k-sparse, but there's some small tail, then my error should be on the same order as the tail. Okay. Yeah. How what? Yeah, how is pi defined? So that's exactly what we're going to talk about, is how can we design. So there are a few questions of interest. In some cases, you can design the measurement matrix, right? So I'm the one who designs the setup, and I get to pick what measurements are being made, and I want to build a device that makes few measurements and does this for me. So I get to pick pi, and then we're gonna write down theorems and prove theorems that say if you pick pi this way, then you can do this. So we're going to show what kinds of pi's work.
Are alphas like big vectors or?
No, so alpha is just a real vector. So just foreshadowing, pi can be, let's say, a random sign matrix, okay, or a random Gaussian matrix, or something that looks like FastJL, or so right. It just turns out that things you've seen before are going to be useful even for this problem. Although the proofs are going to be, it's not just, there's going to be something that needs to be proven, which is very non-trivial, but we'll see the connection soon.
And are K and M related?
Is what related?
The number of measurements and the viscosity, are they?
Yeah, M is going to depend on K. Yeah. So why do I care about this sparsity and approximate sparsity? Well, it shows up all over the place. One of these places is, for example, one of many examples, images. So I have an image, which is pixelated. It's got dimension root n by root n. So this is equal to some x in Rn. This is just view it as a vector. Okay? And okay, I claim that most images, like an image of this classroom, is approximately sparse. Okay? However, it's not approximately sparse in the standard basis. It's approximately sparse once you change the basis. Okay? So also what we'll talk about is basically you can view, so sparse in some basis u, i.e. x is equal to uy, and y is sparse. Y is approximately sparse. Thus, we get measurements pi uy. Okay? Pi x is just pi uy. So in this case, you should think of pi as actually being pi u. Okay? So what is this basis u that images are usually sparse in? Who's heard of the wavelet basis? 1, 2, 3, sort of. Okay, so less than half of you. Images typically sparse in the Haar wavelet basis. Okay. So that basis describes the matrix U. I'm not going to tell you what U is. I'm going to tell you kind of an equivalent way of describing a basis is telling you how to map vectors into that basis. Okay. So if I have an image, which is a root n by root n image, I'll tell you how to transform that image into a new root n by root n image in the Haar wavelet basis. The basic idea is, so pretend, just because this makes things easier, let me actually say the image is actually n by n, and that it's an n squared dimensional vector. Okay? So pretend n is a power of 2. And I'm going to write the image I'm going to pretend that it's actually, well, let me do it like this. Here I wrote it as a bunch of pixels. And here what I'm going to do is I'm going to group the pixels into 2 by 2 blocks. Okay? So so what I mean here is, there's this n by n image I'm actually viewing as being sort of like n over 2 by n over 2. So it's going to be a recursive algorithm that computes the transformation. So this is one block, this is another block, etc. And let me zoom in on one of those blocks. And let me look at the output image. And let me divide the output image into 4 blocks like this, where each one of these is n over 2 by n over 2. Okay, so this is one of those circle things. And I'm labeling the 4 pixels in that 2 by 2 block. And what I'm going to do is, let's say that this is region 1, region 2, region 3, and region 4. And let's say it's this block right here. So that's going to correspond to this pixel right here. Right? It's the second thing in the first row. So those 4 pixels are going to get collapsed down to 1 pixel. What I'm going to do is I'm going to put 1/4 P1 plus P2 plus P3 plus P4 in that spot. I'm going to put 1/4 P1 minus P2 plus P3 minus P4 in this spot. I'm going to put 1/4 P1 minus P3 plus P2 minus P4 in R3. And I'm going to put 1/4 P1 minus P4 plus let's say P4 minus P2. P1 plus. So which guys got minus? P2, P4, P3, P2. So P1, P4, P2. I think that covers all the cases in R4. And then recurse on R1. Okay. So one of these is not like the other. These guys are very similar. Right? I'm basically looking at differences of adjacent pixels. And in an image, in a typical image, neighboring pixels are very similar to each other. Right? Unless it's like on the boundary of different objects. So when you're not near the boundary of different objects, this is something very near 0. This is something very near 0. This is very near 0. So these 3 regions are all very near 0. And then the things that you put here are the things that aren't near 0. Right? That's this thing. But then you recurse on this. So if you look at the output image, it sort of looks almost empty over here, and then as you kind of go toward the top left, you start actually seeing stuff. So this output image looks very sparse. Okay. If you imagine that 0 means black, right, then kind of this image looks almost black, and it looks less black with more color as you go toward the top left. So images usually do have this kind of sparsity, approximate sparsity in the wavelet basis. Right? And I mean, that fact is at the heart of why you can do image compression, right? So we have JPEG and things like that. And they take advantage of these facts. OK. So now we want to actually design approaches that can actually do this compression and recovery. So theorem, this is Candice, Romberg, and Tau. 04, actually, is that, let me make sure I'm saying the correct attribution for this. OK, the journal version was in 06, I guess. I don't know why I put 04. And also Donahoe. There exists a pi in Rm by n, where m is something like k log of n over k. And a polytime algorithm, alg, such that if x tilde is equal to the output of the algorithm on pi x. So the pi is the thing that compresses. Alg takes pi x and tries to figure out what x was. Alg doesn't know what x is as its input. Then x tilde minus, let me write it like this, x minus x tilde L2 norm is at most O of 1 over root k times x tail k. Okay. So again, it's some kind of error term that looks like that. Okay. If x actually is k sparse, then this error is 0. If it's close to k sparse, the error depends on basically how big the tail is. And you get away with a number of measurements that primarily depends on k. You have an extra log n factor, log n over k. By the way, if x is actually k sparse, then 2k measurements are necessary and sufficient. Not using this approach, but there's another approach where if I promise you that x actually is k sparse, you can actually find it exactly in 2k measurements, and you can't beat 2k measurements. And this is Prony's method, for example, which I'll probably turn into a p-set problem. Okay, it's from the 1700s. So, you guys know a lot more math than people did in the 1700s. So, you'll be able to proving this thingy or analyzing this thingy is definitely well within your abilities. There'll be plenty of hints on the p-set problem, but we're not going to cover this in class. But it's interesting that once you want to be able to handle noise, which is true in real life signals, right? Like images are not going to be perfectly sparse in the wavelet basis, right? Like if you look at neighboring pixels are not all the same. Otherwise, your image is not very interesting. Okay. Good. But if you want to be able to handle noise, you kind of blow up the number of measurements by an extra log factor. But if you don't care about noise, you can always do this. Okay. So I guess I'll see you all Thursday. We'll actually prove this theorem, and then we'll keep doing other compressed sensing thingies.